All right, now we're going to actually talk about something that's a little bit more lighthearted. How's that sound? Or a little bit lighter topic. This is going to be about 4.2b, the trig identities concept. And really the actual purpose between any of the trig identity concepts is to really find a way to write something in trig a different way. Now we have all kinds of like mnemonics like this in math in general. Like say you want to say, oh, I've got the number 5 and I want to write it a new way. Well, how about if I write it as 25 divided by 5? It's just another way or some format to write something in a different way. Now, the trig identities that we have out there are identity rules that allow you to look at a particular trig function and look at them in a possibly different light. Now, you've seen some of these already in the past, and what I would say is basically understanding some of these basic trig identities is going to be important because there's an entire chapter of chapter 5 that's dedicated to this particular topic. And you'll be very knowledgeable about this probably in the spring semester. But some of the early basic trig identities that we're going to basically see are some that you should probably have seen already, or I may have mentioned in the last 2 videos. First off, tangent can be expressed in a completely different way. We usually like to think of it as y over x, but it could be written as an identity of 2 other trig functions, which in this case would be sine of a over cosine of a. Now, this particular deal, you're like, why do I want to make it more complicated? Well, it actually may make it more complicated in one way and easier in another. Okay? Cotangent, since it's the reciprocal of the tangent idea, would be possibly thought of as x over y. Well, that would mean that you would actually take the concept and flip it, and it would be cosine of a over sine of a. Now, let me show you how you could use those 2 properties right there in a question that you could use next. Now, it says, hey, we've got these 2 answers, fractional answers for both sine and cosine, and they want you to find out what tangent is. Well, you'll be like, well, tangent of a isn't listed right there. But it would be listed in the fact that it's really sine of a over cosine of a would be another way to think of it. And now I could substitute those values in there and make it 3/5 over 4/5. And these 5th parts would actually cancel out by reciprocal. I mean, you flip it over and the 5s would cancel, and you'd end up with 3/4. And that's the answer for tangent. Now, I really wouldn't have to work very hard to get the cotangent of that, because the cotangent is just the reciprocal of tangent. I could probably put that in here too as well. The cotangent is really the 1 over tangent, or tangent flipped over. I guess that's the idea. The cotangent would be ultimately 4 over 3. It would just flip these 2 around. His cosine would end up upstairs and sine would end up downstairs. Now, what if you were doing the guy next door? Let's try this one. Tangent. Oh, the tangent of a would be, in this case, sine root 5 over 3 divided by 2 over 3. And again, this guy would reciprocate. Some people need to actually see this, and that's okay. They would cancel, and you'd end up with the square root of 5 over 2. Now be careful. Cotangent in this case would be this guy flipped over, 2 over the square root of 5, which is illegal, as we've all learned. We'd multiply by root 5, and we'd end up with 2 root 5 over 5, and that would be the answer for the cotan. So those identity concepts up above, they do lend a hand in helping you understand what the relationships are. Now, in terms of some reciprocal identities, we've used some of these in the past, and that is that cosecant is related to sine, so that would be the reciprocal identity for cosecant. Secant would be 1 over cosine. Tangent would be 1 over cotangent. That's weird to think about that, but that's really what it is. The reciprocal of cotangent would be tan, and the reciprocal of cotan would be tan. 1 over tangent of A. All right. Now, these reciprocal ones, you're like, well, I made it a little bit harder. I put it all underneath 1. How could that be helpful? Well, they can actually help you possibly cancel things in specific spots. I can't really do anything with cosine of the radian of 3 multiplied by secant of 3, but I could write the secant as 1 over the cosine of the radian of 3. And whoa, lo and behold, these two would cancel top to bottom. Answer 1. Awesome. All right. You guys see how that reciprocal identity allows you to do some cancellation from top to bottom? Cotan would be 1 over the tangent of 230 degrees times tangent of 230 degrees. And that's a top to bottom concept. 1. Wow, we're going good here. What do you think would happen between sine of pi over 7 and secant of pi over 7? Yeah, you're right. This is 1 over sine of pi over 7. And that would cancel with this one, but it'd be 1 there. And times 17 would be 17 times 1, which is 17. Awesome. There's your answer. Okay, so if you ever want to confuse somebody with numbers, that's the way to do it. All right. The more important trig identities that you might run into as well, too, would be specifically the Pythagorean identity. Now, if I can give you any kind of a piece of advice, make sure you know this identity. It's going to keep popping its head up all kinds of places, just like Pythagorean theorem always did in geometry. It's extremely important in trigonometry. Now, as we well know, this is the Pythagorean theorem. We derive that idea because it's x squared plus y squared equals r squared. But in a unit circle like this, the r is always 1. That's why we're going to use the Pythagorean theorem as x squared plus y squared equals 1. Now, what I'm going to do here is I'm going to make a quick substitution, and I'm going to substitute things that completely make sense. X is really cosine of the angle, and y is really sine of the angle. Okay, these are fundamental ideas that we've discussed over the last couple of sections. Okay, so I'm going to substitute cosine of a in for x, and I'm going to substitute sine of a in for y, which would ultimately yield in cosine squared of a plus sine squared of a would equal 1. Now, this is the primary Pythagorean identity, okay? It looks like Pythagorean theorem. It talks like Pythagorean theorem. It's a Pythagorean theorem, okay? Now, what happens, though, is sometimes it actually will show up like a wolf in sheep's clothing. Like, it doesn't look like a Pythagorean theorem, but it is another form of it. Now, I'm always good with saying that I can divide any one of the sides by the same number. If I was dealing with algebra like 3x is equal to 7 or something like that, I'm allowed to divide each side by 3. That's the division property of equality. I'm going to say, instead of dividing each side by 3 all the way across, what if I divided these entire side by cosine squared a all the way across? It wouldn't change the actual value of it, but what it would do, I'm going to divide by cosine squared of a all the way across, it would actually change the original Pythagorean identity into something different. Cosine squared over cosine squared would be 1 plus sine squared over cosine squared. Well, sine over cosine is tangent squared of the angle, and that would be the same equivalent. And 1 over cosine is secant squared of the angle. Now, you see this guy right here? That's a Pythagorean identity too. It's just a different styled one. It turns out that it ends up being the same equivalence. It's divided by cosine squared. Now, if I can divide by cosine squared, I probably could divide the main equation by sine squared of a just as easy. So I'm going to put a bunch of little sine squareds underneath here. And what would you get as another wolf in sheep's clothing, or husky in sheep's clothing? That would be cosine over sine would be cotangent squared of the angle plus sine over sine would be just 1. And then this would also be 1 over sine, which is cosecant, oops, I'm writing that right. Why was I writing cosine? It would be, I want the same color. Cosecant squared theta. And that's not the same color, and I ruined it. Way to go, G. Okay? Now, those are the other two primary Pythagorean theorem identities, and they like to do funky things with these, like they might actually take a deal and do a little bit of algebra on it, and maybe move the 1 to the other side and go, oh, tangent squared of the angle is equal to secant squared of the angle minus 1. Dude, that's the same thing. It's just I move the 1 to the other side. What you really want to kind of get in your brain is that cosine squared and sine squared for sure add up to 1. And then you're going to want to see things like tangents and secants. They go together in the Pythagorean theorem. And cotangents and cosecants go together in the Pythagorean identities. Okay? Now, how that can be useful to you is the following. If I use the main Pythagorean theorem first, and in order to figure out what sine is, assume that this guy's going to lie in the first quadrant. Now later let's make other assumptions of what quadrant they lie in. But in this case, we're going to stay in quadrant 1 to keep the idea simple. Okay? Now, what I can do here is that the Pythagorean identity is cosine squared of the angle plus sine squared of the angle has got to equal 1. Well, I've already got the cosine of the angle, which would mean that that would be 5/6 being substituted in there, but that would be squared. And that would be plus sine squared of the angle would equal 1. Now, do you guys see all I've done is actually plug the value in? Well, all I'm going to do now is do a little algebra on this, and I probably drew it way too big, that this is 25/36, and this is 36/36. I'm just writing another name for 1. And could I subtract that one over to the other side and ultimately result in that sine squared of A is equal to, that one subtracted over there would be 9/36. I just subtracted that one on the other side. Now, it's actually written as a square, which would mean that I need to take the square root, and the answer for sine of A would be the square root of the top, which is 3, and the square root of the bottom, which is 6. And it would be positive because it's in the first quadrant. It wouldn't be negative because it's positive in the first quadrant, based on ASTC. First quadrant, all things are positive. Okay? Now, that would be exactly the same concept for this one. You'd square them and you'd work out the same exact idea. I don't need to do it twice. I think you got the idea. Okay? Now, calculator work-wise, we're going to talk about a little bit of calculator concepts too as well, and making sure that you stay in the correct mode. Checking your mode in Trig is a big deal. You'll be like, oh, what are you working on there? And you'll be like, one kid will get an answer, hey, the answer is 1.5. And another kid will be like, no, it isn't, it's 36. And you'll be like, why are you guys getting 2 answers? And I'll be like, are you in radians or degrees? And being in the correct mode is an incredibly important concept. So you got to really look at these carefully and decide what you're really looking at. So this first one right here says cosine of 2.3. Okay, 2.3 what? Is that 2.3 degrees or is that 2.3 radians? If it doesn't have a degree symbol on it, then that answer is a radian. Okay, so you got to look at things carefully and be like, what am I looking at? Now I'd have to go to my mode in my calculator. I'd want to change it to radians, switch it back over here to the home screen and go cosine of 2.3. And if you don't have it in the correct mode, it won't give you the correct answer. Now, 2.3, oh man, this is going to be a check my deal here. Maybe I need to think about this. All students take calculus. 2.3 gives me an answer of negative 0.666. Oh my gosh, it's the sign of the devil. Okay, we're gonna look past that. And that would be the answer to the angle of 2.3. Now 2.3 happens to be in the second quadrant, which makes sense that cosine would be negative. Okay, that's a little bit dangerous there because your calculator has to think about things a different way. Now, radian or degree. Radian is what we're actually talking about here. Sine of 3.89, that's going to be in the third quadrant, 1, 2, third quadrant, because it's a little bit more than 3.14. Answer is negative 0.680. And does that make sense based on ASTC? ASTC, third quadrant sine should be negative. Looks like we're working in the right spot. Now, if we do the secant question that's over here on the other side, that 432 is actually in degrees. Mode change. You're going to get so fun with this mode thing back and forth that you'll get it under control. And this would be written with the inverses that you've talked about in the past as cosine of 432 on the bottom. 1 divided by cosine of 432, and that answer would be an answer of 3.23 is what the answer would be. Okay? Pretty straightforward. That's how big the angle is. And is it in degrees? Hold on. Yeah, it's in degrees. That's the answer. How about cotangent of pi over 6? Pi over 6 is a radian. Oh, man, I'm back to that mode again. So you always want to ask yourself, what function should I, or what mode should I actually be in? This would be 1 over the tangent of pi over 7, and 1 divided by tan of shift pi divided by 7, close your parentheses, answer 2.077. Okay, we'll get 3 decimal places on that one because that makes it a little bit easier. All right, practice these, guys. You got this under control. 15-minute video. I am a master of disaster.